We humans possess the remarkable ability to be able to match across different lighting conditions, different viewpoints, and so on. Have you ever wondered how we can give robots the same superpowers as us, wherein we can match features across different contexts? In today's episode, we will be demystifying the scale invariant feature transform, or lovingly known as SIFT descriptor. So let's quickly set the problem up again. Imagine that you have two images. In this particular case, they're the same image. It's easy to match. If I rotate the second image, this problem becomes much harder, right? Now let's keep going further. And if I change the illumination of it, the problem becomes even harder. The problem gets exemplified when I basically zoom into the second picture. As a human being, you have no problem matching which point belongs to which point in both the images. That's fairly simple and trivial for us. The question is, how do we enable a computer algorithm to do the same? And we will see that today. Let's look at a single feature point, and we know exactly how we need to move this around to be able to match both of these things. And you can easily do this if I make a game wherein you had to scale the image on the right, then rotate the image on the right, and change the illumination slider to match that on the left. You should be able to easily do that, right? So in other words, when we do a feature or feature descriptor, it should work with irrespective of changes to scale, illumination, viewpoint, and so on. Let's fix these issues one by one, and let's build a computational algorithm to do that right after that. So first question, how do we fix the rotation issue, right? We can say, hey, I'm gonna just pick the dominant orientation on the right image and basically align it to be the vertical one. And as long as I do the same thing for the left one, these two orientations are aligned at that same point. Of course, the trick here is to know how to get the same point, and we will come to that in some time. So now to fix the scale issue, what we can do is we can basically zoom the image in and out and basically select the one which matches most to the image on the left, right? And so we have seen the concept of scale space. We can use something like that. If you do not remember the concept of scale space, I urge you to refer to a couple of videos prior to this. And then what we can do is essentially, instead of changing the shape of the image itself, we can also change the shape of our descriptor, which is the square in this case, to match that of the left image, and then resize the image in the opposite manner to basically account so that it looks the same. Okay, great. And we can basically match the average illumination levels to match the illumination. So remember, we talked about blobs as features, and like I said, I refer you to watch that video again. And these are called as interest points. The reason they are called as interest points rather than corners is that, as you will see later, these do not actually have to be in the corner of any of the points in the image, like the Harris corner detection, because these end up becoming centered with respect to some circular size of the blob. So in blobs as features, these are the things we encode: the location of the blob, which is like the center of that square you see, or the circle technically, and the size of the blob, which is basically how big the size of the square or the circle is, and the orientation, which is the dominant orientation, and then the description or the signature of the blob, which we will encode as a histogram. Okay, so let's look at blobs as big corners. Remember that the word blob here means that it's just a circular entity rather than a binary large object, as we have seen in the morphological lecture. Okay, this is sort of an abuse of a word, but in this context of feature description, blob refers to the size of the circular thing. Okay, so if we zoom in, and this is what it looks like, and we take the dominant orientation, we align the dominant orientation, and then we basically scale it up to match the scales on both, and essentially match the illumination to match it up. If we implement this correctly in the computer algorithm, which we will see how in a second, and we should be able to match features across like these variedly looking images, and it should still be very, very good. Okay, let's put this all together. Remember that we take an image and then we basically want to effectively apply the Laplacian, but we saw from a couple of videos ago, if you don't remember, please watch it. It mentions that the Laplacian can be easily approximated with difference of Gaussians across two scales, right? And instead of using the simple Laplacian of Gaussian, we will basically use something called the normalized Laplacian of Gaussian because it's more robust across multiple scales. So let's look at the scale space. You have the image I, and then you basically apply blurs of different orders, and it would basically highlight features at different scales. This is called the scale space S. It's a function of the location and the sigma, which is the blur parameter or the scale parameter, right? You take the immediate differences between the two scale spaces and you will essentially see different features popping up. I promised you that they're not all the same images, as you will see. And if you want to pause the video for a second and actually inspect the images, you can. And you'll see that the different kinds of things are highlighted. And as you go up the scale from bottom to top, you will essentially see that more blurrier features or more sky-like features get highlighted. As you go lower into the scale space, which is the bottom of the screen in this case, you will see fine-grained tiny features. Remember, the approximation we have used here is the difference of Gaussian is given with this equation. The way you can think about scale space is that, hey, it's a pyramid wherein there are images of different sizes, and if you stack them up, they look like this. And in classical vision literature, this is called the image pyramid or the scale space. Okay, let's continue with our scale space. So what we want to do now is essentially find the maxima across these scale spaces. Okay, the way we will do it is we will basically go look for maxima at each of the scales, and we will take the two neighboring scales because we want to find the maxima where it actually is correct. And because we have limited number of scales, it actually might look like this, where you would see that the actual maxima lies somewhere in between the third and the fourth point, which is the green and the black point. If you just take the simple maxima, which is discrete, you will essentially take the black point. But in reality, we know that when we look at the distribution, if you fit a curve, the actual maxima would be somewhere between the third and the fourth point, which is the green and the black point. So we will pick our favorite function here, we will fit a Gaussian distribution, and then we will pick the mean of the Gaussian distribution as the continuous local maximum, which gives us essentially subpixel accuracy. Remember that we only had 4 or 5 or 8 or 10 scale space values, but the maxima can actually be somewhere in the middle of the scale space values, and this helps us get that without actually incurring a lot of computation power. So what we can do is we can basically take these points, fit a Gaussian distribution, and actually do something like gradient descent and get subpixel localization. And I'll cover gradient descent and advanced optimization concepts in a later episode, so please subscribe for that and like this video. So now what we can do is, after doing all this, we basically get a bunch of points which we will call as the interest point candidates. These are called candidates because we still haven't fully gotten rid of all the noise, and which we want to use. Once getting rid of noise, we want to use that as the interest points. So these interest point candidates, basically when you apply your weak minimum thresholding, which is basically anything like we saw before, anything where the maximum value on that subpixel localization is not that accurate, we will throw them out. And so we are going to remove the weak extrema and we will find the remaining interest points. These interest points, we know exactly what the scale is because it depends on which scale space it is. So the bottom one, you see the smallest square. Again, remember this is a square, but it could also be a circle. On the top one, you see the biggest square, right? And I just want to draw your attention again to the fact that these points do not have to be on a corner. If you look at the topmost one, you will see that the interest point looks like it's somewhere in the middle of the sky. It's nowhere in the corner, but again, at that scale, that is what the value is speaking, right? So the way we do the orientation assignment is actually fairly simple. What we do is we take a histogram of oriented gradient like thing, and we basically patch up every scale space into multiple patches, circular or square or otherwise, and we take essentially the dominant orientation from that. And this is what it looks like. Okay, this is awesome. This is great. We constructed a descriptor. How do we actually match them? Right? So let's take a simple example. For each of these descriptors, we basically take the histogram of oriented features. If you don't know what I'm talking about, I would refer you to watch the video on histogram of oriented gradients, which is the previous video, and this would become very intuitive. So for each of the interest point, which is the center of that yellow circle, the main orientation is given by that line where it's oriented, right? But everything else, like you see in these square blocks, that's a feature descriptor. And you can actually like make that into a simple vector, which looks like a histogram of oriented gradients vector. And you have that for every single point in the second image as well. So what we will essentially do is we want to match between the two ones. Let's call them the descriptor D1 and D2 for each point. And you basically take the L2 distance between a point on the left side and a point on the right image, right? So the lower value is a better match. A slightly better way to do the matching is using normalized cross correlation between the descriptors. That also works really, really well. So this brings me to this amazing, one of the most pivotal inventions in the field of computer vision called scale invariant feature transform, or lovingly known as SIFT. This is a contribution by Professor David Lowe, and this SIFT had patent for almost 20 years, and the SIFT patent expired on February 3rd, it expired on March 9th, 2020, and as of Feb 3, 2025, it has been cited over 77,000 times, which is more than a lot of people's careers, right? And this paper is so influential and it's amazing. SIFT is robust. So it's robust to rotation, it's robust to scale changes, it's robust to a lot of clutter, as you see, and it actually works really well in a scenario like this. So imagine we were talking about the Ingenuity helicopter, right? In the previous videos. If you don't remember, I would urge you to watch that. Having something like SIFT or even something more robust would actually be very beneficial in super hard scenarios like that. The question is, did we solve everything? Have we also solved the viewpoint problem, which is the 3D, right? In this particular case, like we have the image on the left, and as we start turning the image, you'll see that the number of feature matches actually go down drastically, right? If you change it a lot more, it's a lot worse, right? So technically with SIFT features, we can do rotation, we can do scale, we can do illumination really well, like changes to these things really well, but not necessarily viewpoint as good. So in the later part of the videos, we will see that we can see a lot better performance with like different kind of feature descriptors. Stay tuned for that and subscribe for that. In this particular 3D example, we see 0 degrees angle between the two images. The second one is 30 degrees and the third it's 90 degrees, and it's drastically dropping, right? Just to quickly recap, what is the scale space? How do you obtain rotation invariance in SIFT? How do you make subpixel accurate feature localization in SIFT? Does SIFT solve 3D feature matching well? Why or why not? See you next time. Take care. Bye-bye.